Hello everybody, it's your friend Daniel here and welcome to another past paper video. In this video we'll be covering Physics Higher Tier Paper 1 for GCSE and we'll be covering the Specimen paper, which is a paper released before the exams are actually sat to allow people to get used to the new content and see what the style of exam questions are going to be. So this is one of the harder papers for GCSE Physics currently out, and without further ado, let's just jump straight into it. Question 1, we're shown figure 1, which is a balloon filled with helium gas, and we're expected to describe the movement of the particles of helium gas inside the balloon. Now you can see with this diagram they're going in a variety of different directions, and the arrow lengths are different. Now, what we need to remember that this means that the gas particles within the balloon are moving with a range of speeds and in different directions, with the mark scheme also accepting that they're moving in random directions, although I'd avoid this because technically nothing can truly be random. And for this question, it's nice and simple to just word it like that, with the model answer for this question being created by me, that the particles of helium gas within the balloon move with a range of speed and move in different directions, with this getting you the 2 marks for the question. Then we jump into the first multiple choice question of the paper, with the question being what name is given to the total kinetic energy and potential energy of all the particles of helium gas in the balloon, with this just being something you need to remember, with the answer of course being internal energy, which you'd just tick the box and you'd get the mark. It's just something you need to remember, unfortunately. Now, for the second part of question 1, it's focused on maths, with 1.3 asking you to write down the equation which links density, mass, and volume, which you get given in your formula book. However, for this specimen paper, formula books weren't given out, they were only given for specific formulas. And 1.4 asking you to work out the density of helium with a given mass and volume. Now, the answer to 1.3 is density equals mass over volume, which, as I said earlier, you can just fetch from your formula book. And for 1.4, it's rather simple. You just plug mass and volume into the density formula to get your density. And for units, if you're dividing mass by volume, it's going to be the units of mass divided by the units of volume, which in this case is kilograms divided by meters cubed, or kilograms over meters cubed. So that's an easy 4 marks right there. Nice maths question to have in the first question of the paper. Now, straight after question 1, which I believe was a rather nice question, we have what I believe is a rather harsh and difficult question on a lesser tested topic. Scientists sometimes replace one scientific model with a different model. For example, in the early 20th century, the plum pudding model of the atom was replaced by the nuclear model of the atom. Explain what led to the plum pudding of the model of the atom being replaced by the nuclear model of the atom. Now this is a lesser tested topic, the history of the atom, with it not being immediately clear what you need to write on, as you need to remember what the nuclear model of the atom is and what experiment led to the nuclear model of the atom, with this being the alpha scattering experiment. So I am just going to show you my model answer that I came up with for this, and then we'll talk through it together. Now, this is an answer which would get you the full 6 marks in the question, and it reads as the following. The plum pudding model was replaced by the nuclear model due to Rutherford's alpha particle scattering experiment. In this experiment, when positively charged alpha particles are shot at a thin gold foil, most alpha particles pass straight through, showing the atom was mostly empty space. A small amount of alpha particles are deflected or reflected off the gold foil, with this both showing the mass is concentrated at the center of the atom and the nucleus is positively charged, with this positive charge also being concentrated in the center of the atom. This differs from the plum pudding model of the atom, which has the mass and charge spread throughout the atom. So basically, for this question, what you need to do is you need to state and explain the experiment which led to the nuclear model being developed, and then you need to show what the experiment showed about the atom that disagreed with the plum pudding model, and then just sort of do a brief comparison between the two models, comparing their characteristics, and that should get you the full 6 marks. This response includes all the marking points on the mark scheme, and it's actually rather short, all things considering, for a 6 marker. and yet it would still get the 6 marks. It's good to just be concise and straight to the point with these questions. Now, question 3 is a data analysis question with it giving you a graph, and it starts by saying the national grid ensures that the supply of electricity always meets the demand of the consumers. Figure 2 shows the output from fossil fuel power stations in the UK varied over a 24-hour period. Now, for the beginning of question 3, as you can see, we just need to do some simple analysis on it, with 3.1 being suggest one reason for the shape of the graph between 3 p.m. and 6 p.m. on Monday, and 3.2 being gas-fired power stations reduce their output when demand for electricity is low. Suggest one time on figure 2 when the demand for electricity was low. Now, for 3.1, the only accepted answer was increased power demand due to people returning home from work and school, as that's 3 p.m. to 6 p.m. is usually when people start to get home from work and school and turn on appliances. However, due to this being a specimen paper, no one actually sat this. So in an actual paper, the range of answers that would be accepted would be larger. And for 3.2, you just look at the point for the graph which has the lowest. I put 2 a.m. They would have accepted anything from midnight to 4 a.m. Now, question 3.3. The national grid ensures that fossil fuel power stations in the UK only produce about 33% of the total electricity they could produce while operating at maximum output. Suggest 2 reasons why. Now, since once again this is a specimen paper, the mark schemes were stricter than they would usually be due to them not having students actually answer it and give their answers. But what I went for was to not cause unnecessary environmental damage and to provide spare capacity due to the unreliable nature of certain renewables. So let's say it's not possible, but suddenly it stops being windy in the UK. The fossil fuel power stations can produce more power to make up for the decrease in the lack of wind power produced from turbines. This is, of course, always hypothetical, as it is always windy in the UK. Now, moving on to question 4, we have another introductory slide, which is annoying because you constantly have to flip back if there's information on this which you need later on in the question. But it says a student investigated how much energy from the sun was incident on the Earth's surface at her location. She put an insulated pan of water in direct sunlight and measured the time it took for the temperature to increase by 0.6 degrees Celsius. The apparatus she used is shown in figure 3, and as you can see, you have a little diagram with solar radiation, sunlight hitting the transparent lid and hitting the water, which is surrounded by insulation to prevent heat getting out, and the radiation would heat up the water, causing the thermometer to increase. Now, for the second multiple choice question of the paper, we're expected to choose the most appropriate resolution for the thermometer used by the student. This is, of course, 0.1 degrees Celsius, because if you're trying to measure an increase in 0.6 degrees Celsius, you're not going to be able to measure it with 0.5 degrees Celsius because it's not precise enough, and you're definitely not going to be able to measure it with 1 degree Celsius because if you want the time for it to go up by 0.6 degrees Celsius and you measure the time for it to go up by 1 degree Celsius, that's almost double the time, with this leading to a massive error in the experiment. Next up, 4.2, 4.3, and 4.4 is like a massive chunk of maths questions, with it starting with you asking to write down the equation which links energy transferred, power, and time, calculate the mean power supplied by the sun to the water in the pan, and calculate the mass of the water the student used in her investigation. Use the correct equation from the physics equation sheet. Their physics equation sheet back when the specimen paper was released only had certain equations. Yours now has all the equations, making it significantly easier for you guys. And here you're given all the numbers you need to use for maths. This in the actual paper is just above it, but I've decided to put it here to make it easier. The energy transferred to the water was 1050 joules. The time taken for the water temp to increase by 0.6 degrees Celsius was 5 minutes, or 300 seconds. 5 times 60 equals 300. And the specific heat capacity of the water is 4200 joules per kilogram Celsius. Okay, starting off, we have power equals energy transferred over time. Once again, just retrieve that from your formula booklet. Now, for 4.3, for the mean power, you just sub in um 1050, and then you divide it by 300, or like 5 times 60, because 5 minutes is 300 seconds. And then for 4.4, you do you get the formula from the formula book. Energy equals mass times specific heat capacity times change in temperature. So 1050 equals 0.6 times 4200 times mass, and then you divide 1050 by 4200 times 0.6 to get the mass of it. Simple rearranging, and that gets you the answers of the power equaling 3.4 watts and the mass of the water equaling 0.417 kilograms. And usually always give your answers to three significant figures for physics. Now, moving on from the maths, quite often they do this. They have a question where they want you to explain why the mean power is only an estimate. Well, there's many reasons why this could be, but the one I went for is that the intensity of the solar radiation may vary over the 5 minutes, because as they're recording the intensity of the solar radiation using the change in temperature water, there could be a cloud that temporarily blocks the sun for half of it, so it may only be like an estimate of what the true intensity of the solar radiation is. Next up, we're given an investigation where a student investigates the efficiency of a motor, and they do this by using the motor to lift a weight of 2.5 newtons, and then measuring the speed, and then using this to calculate the efficiency of the energy transfer from the electric energy stores of the motor to the kinetic energy stores of the weight. And then we start off with a couple of questions which are fairly standard for, in fact, all the sciences, where you just have to comment on the experiment. And it starts off, give one variable that the student controlled in this investigation, and then give two reasons for taking repeat readings in an investigation, with these being questions that could appear in all sciences. Of course, when you're being asked to look for a variable that's controlled, that's quite often called a control variable, and that's just anything that's staying the same. And because in this experiment the student is consistently lifting a weight of 2.5 newtons, one of the control variables is the weight lifted. And two reasons for taking repeat readings is to calculate a mean and to spot and remove anomalies, with this being standard in investigations, and you are expected to know this for the GCSE sciences. Then carrying on from commenting on the experiment, we have a simple data analysis question where we're given a graph of speed against efficiency. And then carrying on, we just have a couple of questions on the graph, starting off with 5.3, which is give two conclusions that could be made from the data in figure 5. 5.4, give the main way that the motor is likely to waste energy. And then 5.5, when the total power output from the motor was 5 watts, the motor could not lift the 2.5 Newton weight, state the efficiency of the motor. Now from the graph earlier on, we could easily see that as speed increases, so does efficiency. However, efficiency does seem to have a limit and only increases to a fixed amount, which could be seen from the graph as the graph began to plateau off. And of course, we know that efficiency can't go beyond 100%. So the theoretical limit would probably be 100%, but from the graph it would probably increase to like 70%, because a motor can't really be 100% efficient. The main way that a motor is likely to waste energy is due to heat lost to the surroundings, with this heating up the environment, and this could be due to things like friction between components of the motor, which turns to heat, and other things like that. And for 5.5, when the power output was 5 watts, the motor cannot lift the weight. That means that 0% of the 5 watts is being turned. Once again, for question 6, we're given a nice little prelude to the actual questions where they just explain a bit of physics. With here, they explain a Van de Graaff generator, saying that it's used to investigate static electricity. Before it's switched on, the metal dome has no net charge. However, after it's switched on, the metal dome becomes positively charged. And 6.1's directly linked to the Van de Graaff generator explain how an uncharged object may become positively charged. Now, in my personal opinion, this is a bit ridiculous, but it's all you need to get the 3 marks. Just one sentence which states that electrons which are negatively charged are transferred from a neutral object, causing a neutral object to become positively charged. Absolutely ridiculous that this is 3 marks, but other than that, it's a nice, simple question. Carrying on, we're shown a plan view of the dome of the Van de Graaff generator, and we're expected to draw the electric field pattern around the metal dome when it is isolated from its surroundings. Now, as you can see, because it's a positively charged, the electric field lines are going outwards, and they need to be perpendicular to the circle, so they're just pointing out from each angle. Now, obviously, in an actual exam, use a ruler. I couldn't use a ruler because I was doing this online, but yeah. Then we're shown a variety of particles or charged objects within the electric field of the magnetic dome, and we're asked which would experience the greatest force. Now, you'd know from like any simple formula or just general knowledge that the closer it is to the positively charged dome, the greater the force is, so the answer would be Q because that is the closest to the dome. Then beginning question 7, we're just showing a simple electrical circuit with a 12-volt cell, 3 resistors with a switch that is parallel to one 60 ohm resistor and an ammeter. Then, as expected, we're given a series of questions on the circuit, with the first one being that the ammeter displays a reading of 0.1 amps. Calculate the potential difference across the 45 ohm resistor. Calculate the resistance of the resistor labeled R, and state what happens to the total resistance of the circuit and the current through the circuit when S is closed. Okay, starting off with the answers for the questions. For 7.1, you just need to use the formula in your formula book, V equals IR, 2 times 0.1 by 45 to get 4.5. For 7.2, you need to do V equals IR, rearrange for V, so R equals V over I, to get the total resistance of the circuit, which is 120 ohms, since you have both the current of the circuit, which is 0.1, and the total voltage of the circuit, which is 12 volts. And then you need to do 120 minus 60 minus 45, because you have a resistor that's 60 ohms and a resistor that's 15 ohms, and they'd all add up to 120, and then you get 15 ohms for resistor R. And then for 7.3, when the total resistance of the circuit, when switch S is closed, the total resistance of the circuit would decrease, and the current of this circuit would increase. Sorry about that, it's meant to say increase. This is due to basically you're opening up, using the water metaphor, you're opening up another pathway for water to flow through, which means the total resistance to the water will decrease and the total flow of water would increase. Next up in question 8, it's about how current varies with potential difference for 2 different lamps, and as we can see, the results are shown in figure 10. And then for the first question in question 8, we're expected to complete the circuit diagram to show how the students could have obtained the results shown in figure 10. And this is the sort of circuit you'd be expected to draw, and how this works is that as you change the variable resistance, the overall current changes, and because overall voltage throughout the circuit is constant, the variable resistor takes up a greater proportion of voltage, so the lamp takes up less voltage, and this allows you to vary the voltage and current of the circuit and of the lamp. Okay, next up they're asking which lamp will be brighter at any potential difference and asking for an explanation. And they're expecting us to use figure 10, which was the graph I showed you earlier for this. And the answer for this question is that A is brighter, and this is due to having a higher current at any potential difference, which leads to a higher power output, which means more energy is being turned into light energy. This is due to, as I showed you earlier on the graph, for any given current, A had a lot higher potential difference. Now, moving on, lamp B has the high resistance at any potential difference. Explain how figure 10 shows this. Now, as stated in 8.2, lamp A has a higher current for any given potential difference, and since R equals V over I, a higher current means a lower resistance, which means that lamp B has a higher resistance at any potential difference due to the lower current. Now, I'm just going to show the answer straight away for 8.4 because it's not a very good question. It asks through which range of voltages both lamps act like ohmic conductors, which means they have a constant resistance, which is shown as a straight line through the origin. And this is a horrible question since the range for which they're straight lines is so small. And it says 0 to 2. But that's just not true because if you have a look at the graphs, if you like draw a straight line from like 0 to 2, it still curves. It's just not a good question, and it's a specimen paper, so it was their first try at making the paper to specification, so it does have errors like this. Next up with question 9, we're showing that a student is modelling the random nature of radioactive decay using 100 dice. He rolls the dices and then removes any which lands on 6. He then rolls the remaining dice until there's none left. And you can see in the table the results of his experiment. Starting off with 9.1, we're expected to give 2 reasons why the rolling of dice is a good model for the random nature of radioactive decay. And the 2 reasons that I went for, and in fact the main 2 reasons, is that you cannot predict which dice will decay, and you cannot predict when any singular dice will decay, with this matching the nature of radioactive decay where you cannot predict which nuclei will decay, and you cannot predict when any single nuclei will decay. Okay, then we are given the student's results as a graph, and we're expected to work out a half-life of the dice. Now you can see for this, when we have the half-life, because we started off with 100 dice, one half-life would be when we have 50 dice left, and you just go along from 50 dice and down to see how many rolls it takes, and it's 3.6 rolls is the half-life for dice. Now for 9.3, we're expected to find the atomic number of thorium after it undergoes alpha decay. And as you can remember, probably will remember, alpha decay, an alpha particle is a helium atom, a helium nuclei. So it has an atomic number of 2, which means the atomic number of uranium will go down by 2, which means the atomic number of thorium is 90. Now, next question is just another 1 marker where they expect you to work out what element X is using information from figure 12 and figure 13. Now, as you may remember from the earlier question, uranium has an atomic number of 92, so it's just uranium. It's not a very good question, to be honest, but 3 marks, who's complaining? Now, the next question is a fairly nice 2 marker asking you to determine the type of radiation as protactinium decays into a new element. And we know it's beta radiation as the proton number has gone up by 1, which is just fairly simple. You can tell from figure 13, and that's all you need to say to get to 2 marks. Once again, a nice 2 mark. Now, moving on to a slightly more experimental, tricky question, 9.6. The teacher wears polythene gloves as a safety precaution when handling radioactive materials. The polythene glove does not stop the teacher's hands from being irradiated. Explain why the teacher wears the gloves. Now, every time I do this question with a student, they always say it prevents the hands from experiencing radiation damage, which it specifically says in the question. It does not stop the teacher's hands from being irradiated. You need to think a bit more critically to work out that the answer is actually that the gloves prevent radioactive material from getting onto the teacher's hand, which would cause irradiation over a prolonged period of time. Let's, for example, say a bit of dust falls off the radioactive source because it's like a dusty rock or something. If it falls onto the gloves, when you remove the gloves, your hands will stop experiencing radiation. However, if you're not wearing any gloves, the radioactive material will stay on your hands for a prolonged period of time, causing additional damage. Now, moving on to question 10, nearly at the end of the paper. Electricity is generated in a nuclear power station. Fission is the process by which energy is released in a nuclear reactor. Figure 14 shows the first part of the nuclear fission reaction. Complete figure 14 to show how the fission process starts a chain reaction. Now you're just expected to draw a simple diagram, such as the one I am about to show. Now this is the sort of diagram you're expected to draw. It's a bit blurry, but it covers the general idea. As a neutron hits a nuclei, it splits into two daughter nuclei, or multiple daughter nuclei, and more neutrons. These neutrons then go to hit other nuclei, splitting them up, and as more neutrons are produced, the reaction speeds up, producing more and more energy. Next up, question 10.2. In the nuclear reactor, a chain reaction occurs which causes neutrons to be released. The control rods absorb neutrons. The control rods can be moved up and down. Explain how the energy released by the chain reaction is affected by moving the control rods. And the answer for this question is that by lowering the control rods, more neutrons are absorbed, slowing the chain reaction, causing the amount of energy released to decrease. Next up, we're given a graph of the power output against time if the control rods were completely removed from the nuclear reactor, and we're expected to calculate the rate of increase of power output at 10 minutes. Now, to calculate the rate of increase of power at 10 minutes, you're going to want the gradient at 10 minutes, and you can do this by drawing a tangent, with the gradient being the change in y over the change in x. Now, the change in y is 2000, and the change in x is 8, which leads to a rate of increase of power output of 215 megawatts per minute, with them accepting anything within a range of 240 to 270. So don't worry if you've got something slightly different. Okay, moving on to question 11. Figure 17 shows a student before and after a bungee jump. The bungee cord has an unstretched length of 20 meters. The mass of the student is 50 kilograms and the gravitational field strength is 9.8 newtons per kilograms. And they just give you a little diagram of what it looks like, and then you'll be expected to ask a couple questions on it. Okay, starting off with question 11.1, write down the equation which links gravitational field strength, gravitational potential energy, height, and mass, which is that gravitational potential energy equals mass times gravitational field strength times height, which is just in your formula book, although it wasn't in the formula book when this paper was created. And then for 11.2, calculate the change in gravitational potential energy from the position where the student jumps to the point 20 meters below. And you just sub in the mass of the student, which is 50, the gravitational field strength, which is 9.8, and the height, which is 20 meters, and you get a change in gravitational potential energy of 9,800 joules. Now, moving on to 11.3 and 11.4, 80% of this change in gravitational potential energy has been transferred to the student's kinetic energy store. How much has the student's kinetic energy store increased after falling 20 meters? And 11.4, calculate the speed of the student after falling 20 meters. Now, the answer for 11.3 is just the answer for 11.2 times 0.8, because 80% of the energy has been transferred to kinetic energy, and that gets you an answer of 7,840. And for 11.4, for calculating the speed after falling 20 meters, you just set the kinetic energy equal to 7,840, and because kinetic energy is equal to 1 over 2 mv squared, you can divide the kinetic energy by 25, which is a half times 50, to get v squared, and just square root that to get your answer. And because it asks you to give it to two significant figures, you round 17.7 and then just a bunch of decimals to 18. Okay, now for the last part of question 11, 11.5. At the lowest point in the jump, the energy stored by the stretched bungee cord is 24.5 kilojoules. The bungee cord behaves like a spring. Calculate the spring constant of the bungee cord. And as always, they give you the formula in the formula book for this question. Now, the formula for elastic potential energy is 1/2 times spring constant times extension squared. And because it has a natural length of 20 meters and it goes down to 55 meters, the extension is 35 squared. So that means you set 24.5 kilojoules or 24,500 kilojoules to 1 over 2 times 35 squared times K, which means that K is equal to 24,500 over a half times 35 squared. You can just plug that into your calculator and get the answer for the spring constant, which is 40 newtons per meter. Now on to the second to last question, question 12. A student wants to calculate the two densities of the object shown in figure 18, which is a metal cube and a small statue. Describe the methods that the student should use to calculate the densities of the two objects. This is a 6-mark extended answer question. I'm just going to go through my written answer, starting off with the metal cube. For the metal cube, you measure the mass using a balance or a scale, and then you measure the length of the cube sides with a ruler, and then cube the side to calculate the volume, and then use the formula rho equals mv to calculate its density. And for the small statue, you measure the mass using a scale of balance, same as the metal cube, and then immerse the small statue in a measuring glass or beaker and work out the increase in volume of water or the water displaced. And this is the volume of the small statue. And then the student could use the formula density equals mass over volume to calculate its density. Usually I'd recommend writing about the Eureka can. So you just put it in and then some water comes out of the Eureka can and then that's the volume of it. However, because this is a specimen paper, that isn't included on the mark scheme. However, it would almost certainly be included in any papers that you would be sitting. Okay, moving on to the last question, question 13. There is a little diagram for this one. However, it isn't needed for any of the actual questions because AQA is just like that. 13.1. If the electrician touches a live wire, he will receive an electric shock. Explain why. Okay. The answer is because the voltage of the live wire is 230 volts compared to the voltage of the electrician, which is 0 volts because people don't have potential differences. This large potential difference causes current to flow through the electrician's body, causing an electrician shock. Now, you may be wondering how you're expected to know that the voltage of the live wire is 230 volts, considering that wasn't stated. However, it is required knowledge to both know the voltage and the frequency of the national grid. Okay, moving on to 13.2, we're given a graph of the maximum power output in kilowatts on the y-axis and the cross-sectional area in millimeters squared of the x-axis. And we are given that the shower has a power output of 13.8 kilowatts, and we're meant to determine the diameter of the wire that should be used for it. Now, you can just go across from 13.8 kilowatts to the cross-sectional area of the wire, which is 9.75 millimeters squared. And then they're nice enough to give you a formula to work out the diameter, which is just the square root of 4a over pi, and then you can just sub in 4 times 9.75 over pi, square rooted to get the diameter, which is 3.52 millimeters. Okay, moving on to the last question. 13.3. The charge that flows through the new shower in 300 seconds is 18,000 coulombs. The new electric shower has a power of 13.8 kilowatts. Calculate the resistance of the heating element in the new shower. Because the question states we have to write down any equations, I start off with charge equals current times time, which means that 18,000 equals 300 times the current, which means that the current is 60 amps. And then you're given in this formula in the formula booklet that power is equal to current squared times resistance, which means that 13,800 equals 60 squared times resistance, which means that the resistance of the heating element is 13,800 over 60 squared, or 3.83 ohms. This is it's a hard question to end on because you have to use a lot of formula, but it is worth 5 marks, and even if you're not able to fully attempt a question, it's worth just writing out formulas and to start subbing in numbers in, because the working marks are rather lenient. Anyways, that is the end of this past paper walkthrough. Just a quick reminder that it was the specimen paper, which means that no one actually sat it, and in my personal opinion, it is the hardest GCSE physics paper that AQA has created. This has been the higher tier single science paper, and if you enjoyed this video, if you found it helpful, make sure to like and subscribe, and turn on notifications so you can get more past paper walkthroughs to help you in the future. Thank you for tuning in, and I'll see you guys later.